folks. All right, last lecture video here for chapter 7. Oh wait, that was weak sauce. You thought I forgot about my air horn. I didn't forget about my air horn. Okie dokie, so let's wrap this thing up, folks. So continuing along with Heisenberg uncertainty principle. The specific form, the more like famous form, is position and momentum, okay? And what this says is, if position is precisely defined with a large number of superpositions, and remember, the way I can define this with a large number of superpositions is by the following, right? Here, maybe I only have a wave function defined by one superposition, but now as I add more and more and more and more, right, I get more and more precise observation of where the particle is, right? So this delta x here for this particular wave function is very small. Consequently, because Heisenberg says the spread in momentum, or really the uncertainty in momentum times the uncertainty in position, must be greater than or equal to 1/2 h bar, right? As one of these gets smaller, the other has to get bigger, and vice versa, okay? So now, this Heisenberg, as far as momentum and position, that's very specific. As it turns out, Heisenberg is more general, okay? So this is our general Heisenberg term, okay? And so the uncertainty principle is, it applies to any pair of observables that are called complementary. So position and momentum, those are complementary observables, okay? So how do we know if two observables are complementary? Well, they must have this following property, okay? So for example, if we keep working in this position and momentum example, you know, suppose my omega 1 is a position operator and my omega 2 maybe is the momentum operator, right? So these are complementary if, okay? Omega 2 operates on psi first. Then after we carry out that operation, omega 1 operates on the result of omega 2 operating on psi, right? So first omega 2 operates on psi, we get an eigenvalue and the original wave function. Then omega 1 operates on that already carried out operation. So now if we reverse the order of that situation and the two are not equal to each other, then they are complementary, okay? And we say that these two observables do not commute, okay? And the commutator of these observables is now the difference between those two operations, right? So for example, if this left-hand side of the equation equaled this right-hand side of the equation, right? Follow me here. So let's suppose that this was not a does not equal sign, but it were an equal sign, all right? So now if we subtract those two differences, right, and keep in mind, right, look, this side of the equation, this omega 1 operating on the operation of omega 2 operating on psi, right, it's the same thing that I've got here, minus the switch of order, okay? Well, if these two things were identical, then this would just equal 0, okay? And so if those two things were 0, then what would happen here, all right? So what we've got is now this chunk of the general form of Heisenberg. Let me highlight this whole thing. So it's 1/2 times this whole chunk, okay? So this is what we have going on here. It's the absolute value of the root mean square, okay, of the commutator. So that's what this whole chunk is. It's the absolute value of the RMS of the commutator. So if these two observables were to commute, so in other words, if this side of the equation equaled this side of the equation, then if I were to subtract the difference of those two, that would be 0. And so that means omega 1, the uncertainty in omega 1, so that's how this should really go, is this should really be the uncertainty of operator 1 times uncertainty of operator 2. Well, that chunk would would be 0, right? And so what that means is anything times another thing will always be greater than or equal to 0, especially considering if the uncertainty of the operator were 0, right? So in other words, if we had no uncertainty, this just becomes 0 is greater than or equal to 0, which is true. Okay. However, if these do not commute, in other words, if there's a non-zero value between this thing, right? So if we'll say if this does not equal 0, then it is suspect to Heisenberg uncertainty. Okay. So for example, so I think, let me see if I wrote up enough space. So I'll give you an example up here. Okay. So when I write this as bracket x position, comma, momentum, and for now, right, we're just doing things in one dimension. So this means commutator, okay? Just like you can see I have right here, right, there's bracket observable 1, comma, observable 2, bracket. So that's my commutator. As it turns out for position and momentum, this is equal to I h bar, okay? And so how do I get that? Well, I get that from the following. So I need to go, so I'm going to put it down in this order. So I would say position operates on the operation of momentum on psi, right? So I just said, you know, omega 1, let's call it position, omega 2, let's call it momentum, okay? And I'll just fill this in for you. So the position operator is x. The momentum operator is h bar divided by I d dx, and so that's, right, first derivative of psi of x, okay? So what we would do first is, now, of course, we'd have to know what psi is. We'd have to have a wave function. But we take the first derivative of psi, then we multiply that by h bar over I, then we multiply that result by x. So you can see right away how these two are not going to commute if I change the order of this operation, okay? So now this is going to be, so momentum operator is now h bar over I times d dx. That's my momentum operator, right? And now my position operator is just x times psi of x. And hopefully right away you can see that these two things are not equivalent because there's a chain rule situation going on here. So I'll keep expanding on now this pxx psi x, okay? So the way that this is going to go down now, right, I have to apply the derivative first, or technically I have to say x times psi x, which, boom, there it is, x times psi x. Now I have to take the derivative of that. And when I take the derivative of that, right, there's going to be the chain rule situation, okay? So I'll factor out an h bar over I, because that's just a constant, okay? And so now the first derivative of x is just 1 times psi of x is psi of x, okay? Plus, now remember in the chain rule, I take the x out in front, okay? So that's x. And then now I take the first derivative of psi of x, okay? And so continuing along down here, right, you can see that these two things are not equal to each other. So in other words, here, I'll write this down. So the result of x px psi x, right, was x h bar over I and first derivative of psi. So we can see quite clearly how that does not equal changing the order of operation, h bar over I times the quantity psi x plus x d psi dx, right? And if we wanted to now apply this to the Heisenberg uncertainty principle, right, to get this I h bar, then what we would do is subtract these differences, right? So I would take this quantity minus this quantity, and I'm not going to do that. You should try that for yourselves. Hint, hint, wink, wink. And we should get I h bar. And so now if we were to supply I h bar right here, okay, we would then take the absolute value of the root mean square of that. And right, recall when we take I squared, we get -1, okay? Well, first we would take the square root, then we would take the square. But all the same, we would get -1, but because it's the absolute value, we would now just get 1/2 h bar, which is exactly where that 1/2 h bar comes from, okay? And we will apply the general Heisenberg uncertainty equation to a couple of different observables. So linear momentum and position are complementary. As we shall also see later on in the semester, angular momentum and angle become a pair of complementary observables, okay? So now what I want to do, so that kills it off for the content that's in the book, all right? So be familiar with Heisenberg uncertainty, both the specific and general form. What is not in our book, which I want to provide you some extra information on, is being able to use what's called Bra-Ket notation. And that is useful because it's just going to make writing these complex math equations so easy. So let's go through it. Okay. So this thing, what I'll call the left-hand side, is called a bra, and this right-hand side is called a ket. So oftentimes people say bracket notation, but it is technically bra-ket. More famously, this is called Dirac notation for the scientist Dirac. I'm failing to think of his first name. But Dirac himself came up with this notation. We now more generally call this bra-ket. Okay? So a ket is used specifically for wave functions, and a bra is used for the complex conjugate of that wave function. Okay? So for example, if I write psi of x, okay, and I want to let my audience know that psi of x represents a wave function, then I can put it in a ket, like so, okay? And that tells everybody, at least everybody who's familiar with Dirac bra-ket notation, that we're talking about a wave function. And now what I place in the ket is actually up to me and how I define my functions, perhaps when I'm writing a paper or spelling it out in a presentation. So I could just say psi x in the ket, and we know now that that's a wave function. I could even just put x in a ket, and that would tell me that's a wave function. Or if maybe I wanted to talk about the wave function of state I could even just say this, and that tells my audience, because it's a ket, it's a wave function. And of course, in my written text or in my oral description of this, I would tell my audience, we're talking about state I, and perhaps state I is a wave function. Or, well, I shouldn't say perhaps. Perhaps state I is a ground state. we would definitely know it's a wave function just by putting it in a ket. Okay. Another thing that we could do if we wanted to be really slick, suppose I was talking about the hydrogen 1s orbital, right? I could go H1s like that in a ket. And now most chemists would recognize this as the hydrogen 1s electron wave function. So I've kind of got some freedom of what I want to put in the ket, but the ket means wave function. Okay, so let's talk about the bra. So the bra is for the complex conjugate. So we wrote psi star x as the wave function of psi of x, okay? So I could put that psi star x in the bra, and that tells me that I'm talking about the complex conjugate. I could even just put, you know, x like that if I wanted to. Oops. But really, I don't even have to put the star right there, because if I put this in a bra, that automatically means I'm talking about the complex conjugate. And in this same notation here, right, I could even just say state I, and that would tell me I've got a complex conjugate of state I, and maybe state I is a ground state. Or back to this other example, right? If I wanted to talk about the complex conjugate of the hydrogen 1s orbital, right? I could throw that sucker in a bra, hydrogen 1s, okay? And that tells me I'm dealing with the complex conjugate of the hydrogen 1s orbital. So now how do we apply this to make the math simpler? So for example, when we're talking about the square modulus, so we recognize the square modulus, you know, in one notation, we just wrote this as psi x squared. That tells me it's a square modulus. I really know that the square modulus is technically the integral of psi star psi dx. However, in this bra ket notation, if I write a bra and a ket together, only separated by one line, this means this whole integral. Pretty sweet, okay? And so now let's suppose back to this example, right? Maybe I'm talking about state I. We'll go back, we'll use the state I notation. So if I was writing this, you know, if I just did this right here, just that simple notation. And now suppose that I'm not even dealing with a one-dimensional wave function. Suppose that this is a proper three-dimensional spherical coordinate system, okay? Just by writing I in a bra and a ket, this would actually imply the triple integral of psi I star psi I d tau. It would mean all of that. So this is definitely a very convenient shorthand notation, but we have to recognize what it means, okay? So there's a couple examples that I'm going to work through, and I would encourage you to work through these on your own first to see if you got it. Let me find my cheater notes here. Okay, so express the following in bra ket notation: orthogonality, a normalized wave function, an expectation value, and a basis set of three states I, J, and K. Let's do it. I'm going to go through my notes just to make sure. And if you want to pause to make sure that you're getting it right, try it on your own while I'm kind of flubbing through. Okay, great, I found it. Okay, so let's go for it. Okay, first one I'm going to do orthogonality. Okay, so let's do that right here. All right, so I'll remind you, orthogonality looks like the following. The integral of psi of state I, complex conjugate, psi j d tau equals 0, where I cannot equal j. So how would I express this in bra ket notation? Well, quite simply, I could just say I in a bra, j in a ket with a shared line does not equal to 0. And bam, look how easy that was to notate. Assuming that I know the Dirac Brockett notation, okay? So now what about a normalized wave function? Okay, let's do that over here. So I'll remind you, let's see here, normalization. Okay, if we write what a normalized wave function looks like, let me just make sure that I'm going to write this down correctly. Okay. Okay, great. So I'll remind you, if I have two normalized wave functions, okay, that's integral of psi I star psi I. So I can only normalize wave functions if they are in the same state, okay, d tau, and that equals 1. So this just tells me the wave functions are normalized, okay, right? We know that to find the normalization constant, I would put an n squared out there, okay? And that would allow me to find the normalization constant. But if I just want to tell my audience I have two normalized wave functions, then I can just simply write I equals 1. And just this simple notation tells me a wave function of state I is normalized. All I got to do. Brilliant. Okay. So how about expectation value? So now this is where this one is going to change a little bit. Okay. And so for expectation value, I'll remind you what the mathematical operation is. It is integral of psi I complex conjugate omega, right? We make the operator sandwich, psi I d tau equals lowercase omega, okay? So now I have to change this up just a little bit to write this in Brockett notation. So here's how I do it. I write the complex conjugate in a bra, okay? I make the operator sandwich like so. I put I in a ket, and that all equals lowercase omega, okay? So that's how I could express the expectation value using this shorthand Dirac notation, okay? And then finally, for my basis set, I'll pause for a moment while I'm flipping around for the answers, and you can try to do it on your own. Okay, beautiful. So if I wanted to now, so I'll write out what the mathematical operation of my wave function is. So I'll write psi equals, and so we've notated that that's 3 states, okay? So there's going to be some constant for state I times psi of I plus some constant for state j times psi of j, and some constant for state k times psi of k, okay? And so now, when I write this out in my Dirac notation, it's not really going to be shorter necessarily than how I just wrote it, but it's still going to be a good way I can apply writing this. So I will write that my wave function, so I just put psi in a ket, which is fine, okay? And so now I'm going to say that that's this constant, right? Ci times the wave function of I, okay? Plus this constant of state j times the wave function of j. And notice here now I'm just putting I in the ket because, again, since I've put it in the ket, it tells me it has to be a wave function. And then finally plus ck times some state k. All right? So as we progress through this class, our wave functions are going to get more complicated, all right? Our mathematical operations, this orthogonality, normalization, expectation values, and we will eventually use a basis set. We're going to have to use basis sets to describe the atomic orbitals. Those equations are going to become humongous, too cumbersome to write out. So this Dirac or Brocket notation, both names are okay, whichever you prefer. It's going to become extremely useful, especially if you're writing up your exams or in your Mathematica files, for example, if you want to use this really slick notation to make a nicely formatted answer. But also, as I'm writing out of my lecture notes, it's going to be very practical for being able to write and use this shorthand. Okay? So, as it says in the learning goal, I want you to be able to express the above mathematical operators, or this says, operators should be operations, but basically, be able to use this Brocket notation. Okay, folks, we're going to move on to chapter 8, and it's going to be another gargantuan chapter that takes several weeks to get through. So please make sure you're staying on top of it. Okay, this stuff is heavy, it's difficult, it's weird, and there's really nothing like it that you've learned before. Okay, so good luck. Please reach out to me if you have questions. I'll see you later.